Hi everyone. Well, today I'm gonna be showing you how to do or calculate all the urban demand for the urban water management portion of the class, which is exercise number 2. So at some point you will be here on HydroLearn, and basically here we'll ask you to calculate population projections. So you can do it from here, or this is already on the website of the class, and you might be able to access the same tutorial and sheets here. So let's actually open the tutorial document, which it is this, and also open the Google Sheet template. So now that we have these two, what we're going to do is well, first of all, try to create give me a second. So we will create a copy of this file. So I will go here, make a copy, and in here I will go to my folder of, in this case, exercise 2, and I'm just gonna call it urban and rural template, and here will be some Sandoval. So this will create a copy there. Now in the meantime, this will go back all the way to what we have discussed before. Actually, in here you can also see that these are the very summarized instructions on how to do this exercise. What we want to do here is to estimate the population, in this case of Watsonville, all the way to 2050. So the first thing that is asking us is to first will be to create a plot, and we want to create this plot. And what we're going to do first is select, actually we can do this from the headers, select all the way up to 2020, insert, and then a chart here. And yes, it will come this scatter, and there you go. So we already have this. We can edit the chart, for instance here. Let me see. So the chart title, we can have it as it is there, population, and then what it is asking us is to create a trend line. So we need to go back here to customize, and then I think here in series it comes this that is called trend line, and here in trend line by default it comes linear. So we want to use the one that is called power series, and then here in the label we want to create the equation, and that it shows the R square. What you can see here is that this is putting the equation of this power regression line and the R square. Okay, so basically that's what we have in here. Now, as you can see, this is very similar of what we have in here. Now, what we can do is use this equation to create this specific time series data or prediction of the population using a power law. So in this case in here, I will paste this formula, and what you can see that is already referencing AC. Basically what this equation tells us is that the population put us as population is a dependent variable, and the independent variable is the years. So instead of X, in this case will be in years. So when we click here enter, and then we create here the let's do this. Okay, so far we calculated this value. Okay, now with this equation that is actually referencing this year, we can predict all the way to till 2050. So there you go, here we are. Now here we want to calculate the R square between these two. So basically we will calculate the R square from 1970 till 2020. So we can use, in this cell, we can use this equation. And what you can see here is that it is calculating the how similar or how different are from 1970 to 220 these two data series. And right now what you can see here is that this value is 0.934. Okay, now what we're going to do is to only plot data from 1970 to 220. Okay, and basically we will do exactly the same. And now, and there you go, here we have that data. We can also go here and in customize series we will add once again a trend line, and in this case the trend line that we're gonna use is linear. Once again, that the label is the equation and that it shows R square. Now what this is doing is basically telling us, you can see that now this line fits better the last part, and actually the R square in the last 50 years is quite good, 0.96 and 97.6. The closer to 1 the better. So we can also having here in the chart title, we can have okay, so we have now this specific we can actually have exactly the same title. Population of Watsonville, linear model, sorry. Okay, so now we have that one there. Ta-da! Now we're gonna use this equation to predict the next wait, give me a second, there you go, to predict the data from 1970 all the way to 2050. Something that you're gonna see is that right now is predicting that by 2050 that using the power law model we're gonna have 150,000 people living in Watsonville, which is quite a lot considering that in 2020 it's only 55,000. So I don't think this can be realistic. That's why we are using a different model. Now what we're going to do is in this cell we are going to paste this one, And as you can see, it's actually doing the same. It's using the year as a means to, as an independent variable to predict our population. And we can go all the way here. Great. And we can also do the R square. In this case, the R square has to be from column the observed population, the census population here, versus the predicted population. And there you go. We have it that now is 97.56, which is what we have it in here. So now we have, as you can see, the same similar population as the one that it was put it in here. I mean, sometimes in here is just some of the decimals that you can see in terms of the difference, but that will be good enough. Okay, so let's get going. And now that we have that, well, you will have to submit some of these equations and so on. Now what we're going to be doing is we want to double check. So this has better R square than this one. But how do we know that actually this data is correct? So one way to know it is to see what has been the decadal average. So what we're going to do, so here we're going to insert this, but actually rather let's calculate first the decadal difference, and then from there we will start in here. Let me just hide this. So basically what we're going to be doing is subtracting the previous one. So in order to calculate the decadal growth, we subtract this. Well, actually, this is the historic value. We'll subtract this minus this. And in this case, this will be the historical decadal growth. What this is doing is estimating, in this case, how much of the population grew from 1970 to 1980. And this will be from 1990 to 1980, and so on. We can do exactly the same for the power law model. So basically, here estimate the difference between 1980 and 1970. And the same we can do for the linear model. So you can see here that numbers are quite about the same. These are the difference, of course, because it's a linear model. Here the decadal growth is linear, is the same. We can calculate here the average of the decadal growth for the historic, the power law, and the linear mode. This of course is the same. But what you can see here is that something to kind of verify is that the linear model, the linear prediction, it's closer than the historic prediction, and that the power law model is way higher than the historic prediction. So this is another way to verify that this specific regression might be good for it. So once we have done that, then you will have to submit these questions. Now we will be now switching gears and start calculating. So we calculate first the population. Now we need to calculate the water use per capita. And if we have the population and the water use per capita, then you can estimate the water demand. And in this case, what we're going to be doing is calculating for urban and rural. So this is the data that we have in here for all these different, so this is data of Watsonville and how much water is being withdrawn from 1999 to 2019 from surface water and groundwater sources. So now what we're going to be doing is, well, first is, let's just take a look at it. And in this case, what we can do is something like this, and then just insert chart, and then in here we can have stacked, and for some reason, let me see here. I see. Okay, so we'll basically, this is only having the series of the surface water. So here we're gonna aggregate another one, and we're gonna put here the series of the groundwater and, sorry, okay, let me, okay, so the so we will add first the X time series. So there you go. Now we have it. Now this one, and I'm gonna add the sorry. Okay. No, here. There you go. Okay. And this is the first series of groundwater, and here this will be the series of surface water. Now, if we stack them, ta-da! So that's how we can have one of these. Something also for us to do is, you can see that this is surface water and groundwater. Now here it will tell us to estimate now we want to estimate in here, give me a second, the total use per year, then in gallons per year, and then in gallons per day. And then here we're gonna use the previous linear model to calculate the population and estimate the water use per capita. So in this case, to estimate the total water use, we'll just need to add this plus this. We can do it in that way. See that it is already, it knows that it has to calculate to gallons per year and then gallons per day. That's okay. But basically we can do it like that, or we can use the command zoom. Now what I'm going to do is, there you go. So this has calculated that. Now, for the sake of practicity, I will copy those, but in order to, so these are acre feet per year. In order to convert acre feet per year to gallons per year, then we have to multiply this value times this many gallons per acre foot, which is basically here 1 acre foot equal to this many gallons. So that's why if you multiply this times, there you go. Okay, and now because this is in gallons per year, if you divide this over 365, then you're gonna get that number. Okay, now once we have it like that, we can just, you can go here when you see that it changes from this cursor or this arrow to that cross. That's one way of copy things. So now we have all those values calculated. Great. Now what we need to do is to calculate the population, and the population is actually quite simple, right? So we know that here the population is the year times 840.51 minus that value. And in here we have, yeah, this much. If it is not looking like that, something like that you can do is to use this number, and then there you go. So right now we have it in that format, and we can copy that until here. Up, sorry. There you go. So this should have been done. There you go. Okay. Ta-da! Okay. Now, once we have finished this, which is the series of values that you're seeing here, now what we need to do is to calculate the gallons per capita per day. And basically in this case is the gallons used per day divided by the number of people. And in this case we have 170, and by 2019 now they are using 98 gallons per person per day. Okay, so now you can see that we are going there. Something that we're going to plot is this precipitation versus the water use per capita, to see if there is any correlation with higher years, high wet years and precipitation. So something that I'm going to do is just right there I'm going to plot only the water use per capita. So insert chart, and then in here what I'm going to use is this. For the X series I'm going to use this. So you can see that now everything is lining up, and I'm gonna add another series, and that series will be sorry. Oh, I see. Here I need to add precipitation, but it was just right behind it, so I was not able to add it. So I need to add this precipitation. So in here, add series, this kind of window, and here I need to select this range until here. Okay. And now we have it in here. Now the main issue here is that, well, I mean, we have it, these are in two different units. So the first thing that I'm going to do is to do something like this. And then the following one is that I will go to this one of customize and then series, and then I will use the one of precipitation and line. Right now it's on the left axis, so in order to put it on a secondary axis, I will put it on the other side. So I click here, right axis, and in this case I would like to have a dash line. And ta-da! We have it in there. Here, as as it is kind of here, something that we can do is here it should be water use per capita and precipitation. Watsonville, California. And there you go. Okay. And you can see that here we're just start piling up a lot of our graphs. Great. Now we're gonna do something similar, but now you can see that so here perhaps the one last thing is from this last part we want to estimate what is the average from 2015 to 2019. So here we can type average, and then here we can go (2015) to 2019, and what I hit it is just shift and then the arrows. Now enter, and it got us this number, which that is correct. So we have about 100 gallons per person per day in this kind of 5 years. So here it will come some specific questions for you about some of these years and what's going on with those. And now, and how these values are compared to this, okay, which is the rest of the world, how the United States comparing the average use per capita from the rest of the world. Here we're gonna do something very similar for the rural water use. So the same, first we're going to estimate the water use considering these two water sources, then the total gallons, which it will be multiplying by 325,851, which is gallons per acre feet, and then finally here dividing everything over in 365, so it is to calculate the gallons per day. Once we have these three, then ta-da, we can calculate this. Now, water use per capita, this is kind of tricky because here the population, this is for the two water use, so Watsonville and the rural water use. Now, in here, what we want to do here is that we only have population for 2000, and that will be 17,690, and for 2010 will be this one. So as you can see, the rural population hasn't changed. It's 1,000 more or less, give it or take. So what we're going to do is to use the population of 2020 to calculate the water use per capita. So in this case, we're gonna be dividing this over this population, and in order for this table for not to move, just need to hit F4 and it will bring these kind of dollar signs. With that one, it will fix it up. So you can see yeah, 114, 116, 118, 113, 123. So this is for the last 5 years, right? And then here we'll provide a comparison of how that is going. Okay, now we are going to calculate the indoor and outdoor water use for both urban and rural. Okay, so this first part is the indoor urban water use, and here I explain why. What are those? What are the main uses that we have and some of the different values? This part in here is showing some of the typical values of, for instance, washers, dishwashers, and so on. Okay. So in this case, so here it is explained that much. So in this case, for the laundry, we're going to be using, for the urban, this advanced with wash plates. So we're going to be using this many water uses per day. And basically what you can see here is what we're doing is like units. So what is their load capacity, how many times you're using it per week, and then dividing these ones. So in this case, we're dividing this average consumption per use. You use it 3 days, and we're dividing it over 7 days per week, right? So in order to know how much water is used on a single day, right, on average. This is exactly the same. All of these are doing that specific calculation, because in some of this is not that you use it every day. It's just an estimate for how much you use it per week. So here we go back here. So this is 6.4 gallons per person per day, 1 day. So here the quantity will be equal this times this. So it's about 6.4 gallons per person per day. For the dishwasher, we're gonna be using the one that is 4.7. This guy here. Okay. We use it only one, and then here is the same. Next one, for faucets, we're gonna use faucets that use 2 gallons per minute. And we estimate that we use about 10 minutes per day. Again, that's how much per day. And the same for showers. Showers, ones that use it 2 gallons per minute. And a shower of 10 minutes. Okay, sorry, here it was 6. I got carried away in here. So this was for the use of faucets, and for showers, yeah, we are considering a 10-minute shower. Finally, for toilets, it will be 2.2 gallons per flush. And then we're considering 3 times per day. About 50 gallons per person per day. And now in here what we're going to be doing is estimating what are the main uses. Once again, if we want to fix this one, we can hit F4 and it will get fixed. So as you can see, most of the water, yes, is used in showers. So that will be the easiest way to save water, take shorter showers. And the next one is on the faucets. And then you can see that the toilet, the laundry, and the dishwasher is, and typically we try to replace this, but it's where the less water is used. Now, for the rural baseline indoor, we're gonna do something actually similar. In this case, we are going to be using the laundry. We're gonna be considering a 16.1, meaning that this one here, we're using an old laundry machine. For the next one, it is exactly the same uses. So the 4.7. Here is the faucets, 2 gallons per minute, 2 gallons per minute, and 2.2. So those doesn't change. Here will be 1 day. Faucets, 6 minutes, still people taking a 10 shower minute, and then 3 flushes per day. This will be here. And there you go. So we have a comparison of 10 more gallons basically from rural to urban. Now here we're gonna be, and I will ask you here some things. Then we will estimate the outdoor use, which is basically the landscape. So in here you will have to, I explained here how it is calculated, but basically you multiply ETO, so the reference evapotranspiration, times the crop coefficient for each of these different landscapes. That will give you the evapotranspiration of the landscape for 1 square foot. And then you will have to calculate it for all the area of the backyard and front yard. Then how convert this into gallons per year. And then we're gonna be working with the irrigation efficiency to see how much water is applied. We'll get the outdoor use, the outdoor use per year, indoor use, and that will do is the outdoor use per capita. Well, this will be in gallons per year, gallons per day, and so on. So let's get going on that one. So we will go to CMIS, and in CMIS we will go to this station, station 95, and basically the value that it is in there is, it evaporates 38.67 inches per year. Okay. And according to WCOLS, which is a database, it says that the KC value is 0.8. So the ET of the landscape is this, the multiplication of these two. Okay. Now, in order to estimate the square footage, we are considering about 2,750 square feet. The conversion factor to obtain gallons is 0.6. So in this case, the ET is multiplying these three. So the ET of the landscapes times the area times the conversion factor. So it will be this times this times this. There you go. And now this we will have to divide it by the irrigation efficiency. And we're assuming that there are sprinklers there. So in this case will be the water ET over the efficiency. And yes, we're applying more water because our irrigation system is 70% efficient. If it was 100% efficient, this will have to be the same. Now we need to convert these gallons per year into gallons per day. and basically here we'll have to divide it by 365. I should say there you go. So here we have the 2 gallons. And now, so 2 gallons per day, we're considering 4 people per house. So we're gonna divide this daily use on the landscape over the number of people. And there you go. We have 49.9, a total of 99.6, 99.7 gallons per person per day, roughly 100. And then we have to do the same but for the rural use. These values are the same, so the evapotranspiration doesn't change, nor the crop coefficient. So in this case, here we go with the same value. Now here the area, because we're in the rural sector, it might be a larger landscape, so that's why we have 3,200 square feet. And in this case we'll do exactly the same, multiply, excuse me, we need to multiply these 3. There you go. We are considering the same irrigation system, 70% efficient. So because it is that efficient, we need to use this much gallons to actually irrigate it. We are over irrigating in this case. And you can see that this is happening, for instance, when here we are in the campus, we're seeing that the pavement is well watered. You can see that irrigation systems are not that efficient, so that's why we're considering this value. Here is the same. We'll have to divide this over 365, and then this value over 4 people. So similarly, and here we're comparing it with the previous that we estimated here. Give me a second. Here I forgot to estimate the average of the last 5 years. What you can see in here is that this value that we estimated through this method is very similar as the value that we estimated in here with the overall numbers, and basically it's the last 5 years. Okay, here I'm basically verifying that these values that I estimated before are within the range, reasonably within the range of the values that I'm estimating here. So that will be it. Now, here it wants us to estimate this, the monthly water use, because basically what you're gonna see is that the reference evapotranspiration changes depending on the month. So our water use will not be exactly the same as it is. Multiply, it says here, the ETO times the crop coefficient, which is this KC, times is the square area, this one, and the conversion factor, which is this one. And please remember to hit F4 to create this kind of dollar signs, and that value will get fixed. Then we will copy this. So you can see the numbers are the same, and the sum should be what it was saying here, this. Now for the next column, what we need to do is that this applied water, we have to divide it by the irrigation efficiency in cell M36, which is this one. And it should be about this value. The outdoor water use per capita is divided by the number of people, right? In this case, we are and also by the number of days. So to calculate the water, so this is per month. Let me go back here. So it will be the applied water over here. Sorry, the applied water divided over the number of days, and these two we're gonna divide it by the number of people. There you go. And as you can see here, is about those numbers, right? Now here we can obtain the average, and it will be closer to, sorry, okay, this have to be 49.9, that it was our previous value. These are the indoor water use, and then the total water use will be the sum of these two. As you can see that the water use is not constant throughout the different months. Some months will be way higher and some months will be way lower, and that is because of the different environmental conditions. So we will need to do exactly the same calculations, but now for the urban water demand. So yeah, let's actually do it quite fast. So it will be this times, once again, so this will actually have to multiply. So that is the ETO times the crop coefficient, which is this, times the area, okay, this times the area times the conversion factor. There you go. Then the applied water will be this divided by the irrigation efficiency, and the same. The outdoor water use per capita will be to multiply that column times this, sorry, open up this many gallons per month divided by the number of days, and then divided by 4 people. And then this will be the sum of these two. Yep, it went to our recorded value. So for the last part, now we need to calculate to predict the water demand in the future. So we finish this portion here, and now let's predict the population and the water use per capita until 2050. So the first thing is that we need to recalculate here the population, and this is actually quite simple. Something that you can do is copy this equation, paste it in here. Instead of times year, what you can do is use this one, the year, and then minus these specific values, and then I'll just get rid of the commas just in case. So there you go, we have the first value, and then we can use the same equation to fill the rest of the columns. You can see here that this is actually pretty similar. So that will be for calculating the population. Now that's the first part of the ingredient. If we have the water use per capita, then we calculate the gallons per year and then the acre feet per year. So in this case, this value comes from here. This we are gonna borrow them from our previous section. So basically what we're going to do is to go here to, in this case the indoor should be projected water demand. Here we have this summary in here, if I remember correct. See, we have for urban, we have this, so we can do the same here, and then here we can do the sum of these two. And just so it has a nice format, we can paste the format here. And now for the rural, we can do exactly the same. Come back here and then estimate the rural and do the same. And then we are gonna borrow the format from here to here. There you go. We can also estimate this by the percentage by dividing this value, the indoor, over the total value. Remember to hit F4. And this one we want to have it actually as percentage. Once again, we can borrow this format. Oh, sorry. There you go, percentage. And we're gonna get rid of the decimals. And here we can do, let's actually just do it pretty fast. Okay. And let's just once again copy the format here. There you go. So we have these values already here. Now what we're going to do, well, here is a part for you to be turned in. Now what I'm going to do is to put in 2020, I'm gonna use this value of 100 gallons per person per day, and I will expand this value, or think that this is gonna be a constant value all the way to 2050. That's a policy that I want to implement there. After that, what we're going to do is multiply this population times gallons per person per day times 365 days per year. And this will give us gallons per year, so it will be this times, there you go. Let's do the same here. So this times 365, and these two, I really want them to have it, but I want to have a different format, one that actually has commas and that it doesn't have decimal points. Ta-da! Have it all the way down here. And now what we're going to do is to divide this over this number, which is the number of gallons per acre foot. So it will be this one divided by that value. The same. There you go. So we have it all the way until here. And these are close enough. It's 9137, 9141, and so on. So we have it in there. For the population in this one, we're just gonna consider the population that we have in 2010, which is this much people. I can actually go in here and look for that specific population, which we know is this value, and I can hit F4 and fix that value here, and then do the same, just make equal to the previous one, and taran, we have it all the way there. And we're gonna also consider that here in 2020 it will be this 117, that will be our water use per capita, and that we're gonna conserve that water use per capita until 2050. And remember that this is for planning purposes. A lot of these things we're just thinking how we're gonna do this in planning. Likewise, we're gonna multiply this, so the population times the water use per capita times 365, because we have this is per person per day, so we need to complete now this one by that, and I'm just gonna change the format here to something that, and this is gonna be a constant. Well, in some parts it will not be that constant, but from here on is a constant value, right? Finally, what we're going to do is the same. We're going to this one divide over that number in order to have acre feet per year. 2235, this is 2036, close enough. And then we'll need to do this stacked column. Something that you can do here is do here urban, and then hit for rural, and then just select these two. Here you can use control and then drag the cursor all the way down there. So you can you just press control and keep the control key put down until you drag it and select all what you want. Now that these two are selected, you can go here to insert chart, and I think this is stacked. It is coming. So here we have it in columns, so we can put them stacked. And of course this one, first it came the rural on top and here the urban, and in this is all the way around, right? The urban is below and so on. That's okay. What we want to know is this a specific trend. So and for the x-axis, what we can do is to go all the way here and select this one. Okay. And let's see. Oh, I know what is happening. So actually this one, let's just, in this case what I'm going to do is to here, yeah, here I'm just gonna put here, because it was the these three were put together, that's why this axis is not correct. So we're going to go back here, edit chart, and when it comes this, we can remove, and then we're gonna here add the axis, and now, sorry, just select a range, so it's gonna be this one, okay, and ta-da! Yeah, happy face. And you can add, so for instance, you can add all these values, right? So here in customize axis titles, you can put here baseline, urban and rural water demand, and then that will be it. For the vertical axis title, we can also put in here water demand. This will be acre feet per year, and there you have it, and so on. Okay, so we have now this specific one. So here now we are going to, in this one it's already reading where this data come from. But basically this data, if you remember, it comes from the urban water demand. This should come from the values that we already calculated. So here, this one should come, if you remember, from here, right? And then we can drag this out. So this 182, 121, so we have already calculated this, right? This one will be multiplying this value here. So remember that we calculated this one back then here. So these are the total water use. We wanted now to calculate it in acre feet per year, right? Excuse me, just in acre feet. So it will be multiplying this value times the number, so the water use per capita times the number of days, M16 times, give me a second, this value, which is basically, in this case, the annual demand for 2020. And because this is, so this is the population, so the water use per capita times the population on that day times the numbers of days, that will give us the total number of gallons, divided by this, which is the conversion factor from gallons to acre feet. It will give us the acre feet, and this will give us actually how many acre feet per we need every month. This value should be similarly not equal to this one, which is the water demand on 2020, the annual demand on 2020 for this specific year, because we were using the year 2020 for estimating this specific monthly distribution. We'll do exactly the same, so multiply the water use per capita per the number of days times the population in 2020, and that will give us the volume of water in gallons, and then here we divide it over this much, which is the conversion from gallons to acre feet, and will give us this specific acre feet per month. This should be equal to this value, which is the annual water demand for urban use, and that will do it here. Then, so as you can see, we have all of those here. Yeah, this is close enough. 6416, 6419. Now you need to create this table, but basically, in this case, so you can put it in here. Urban, and then here you can put rural, and then sorry, there you go. So what you can do is select this, control, and then drag the cursor, select that, and then insert chart, and there you go, right? And if we want to add the x-axis, then we'll go here and add the months, and ta-da! You can also continue adding the specific title of the x-axis and so on. So that will be it for this exercise. Thank you. I'll see you in class.